Numerical Computation, Chapter 7, Extra Video Number 1. You can view this video after you have completed all the regular videos for this chapter. We study systems of nonlinear equations. Consider a system of nonlinear equations in the general form. One can write it out for each equation. f1, depending on n variables x1, x2 to xn equals 0, and there are n of such equations. Perhaps it's more convenient to write in a vector notation than one has a compact expression, capital F of vector x equals 0. Here, capital F is a vector valued function denoting the vector of functions f1, f2 to fn, and then x vector is the collection of all the unknowns. We discussed two methods, the fixed point iteration and Newton's method. In this video, we look at fixed point iterations, and the next video we will look at Newton's method. We are perhaps familiar with fixed point iterations for a nonlinear equation of one single equation. Now we extend the idea to systems, that is, n equations. So given a function, capital F of x equals 0, we find another function, capital G, such that f of x equals 0 if and only if x equals g of x. Now such a function g can always be constructed, and here we give two rather trivial examples. You can put g to be x minus f of x, or g to be x plus f of x. And then, given an initial guess x0, one perform the fixed point iteration for x equals gx. That is, at step k, xk plus 1 is computed to be g evaluated at xk. So this looks almost identical to the case for one single equations, except now we replace the x with the x vector, and the function g now is a vector valued function. Similarly, one can implement stop criteria to be the combination of any of the followings. So given epsilon, which is the error tolerance, if after performing one step the difference between the two vectors measured in some vector norm is less than the tolerance, the second one will be the residual measured in some vector norm is less than the tolerance, and the third one will be if a maximum number of iteration is reached. Let's take a look at convergence. Of course, the convergence depends on properties of the function g. Let's introduce a concept called a contraction. Assume that the function g is a contraction, which is defined as follows. G of x minus g of y measured in some vector norm is less than a positive number a here multiplied by x minus y measured in the vector norm. And this number a is positive and shall be strictly less than 1, and this relation should hold for any vector x and y. So this basically says, taking 2 points x and y with some distance between them, and then you apply g onto them to obtain two new vectors, and they would actually be closer to each other than the original vectors. We now check the distance between xk plus 1 and xk. So we have this norm equals xk plus 1 is computed as g at xk, and xk is computed at g at xk minus 1. And then we use the contraction property as here, putting x to be xk and y to be xk minus 1, and this shall be less than a times the norm of xk minus 1. So this is a iteration relation. By simple induction argument, we reach that xk plus 1 minus xk in the norm will be less than a to the power k of the distance between x1 and x0. Therefore, xk form a Cauchy sequence, and by standard analysis theorem, this converges to a unique limit. And next, we need to show that this limit is the fixed point. Let R be a fixed point such that gr equals R. We now compute the distance between xk plus 1 and R, measured in the norm. This equals g at xk, which is xk plus 1, and R, we replace it with gr since that's a fixed point. Then we use the contraction. This distance is less than a times the distance of the two variables sending to g, so xk minus r. We see again this is a recursion relationship. Again, one apply a simple induction argument to get that xk minus r norm will be less than a to the k times x0 minus r. Now recall that by the contraction principle, this a here is a positive number strictly less than 1. Then as k goes to infinity, this coefficient here goes to 0, and the norm goes to 0, and we say that xk converges to r. If you consider the distance here as the arrow, and you see arrow at k plus 1 is bounded by a number times arrow at k. Therefore, we have a linear convergence. One can also derive some interesting a posteriori estimates. We observe that by the triangle inequality, we have x0 minus r in vector norm is less than x1 minus r plus x1 minus x0, measured in the norm. Then, by our previous analysis, we know that x1 minus r in the norm is less than a, the contraction constant, times x0 minus r. So if we replace this by that, we keep the inequality. Then here we see that these two terms are the same, so we could move this to the left and get a 1 minus a, and then we can move the 1 and minus a to the right. So this gives us this following inequality. So the initial arrow is bounded by 1 over 1 minus a times the distance between the first iteration and the initial data. We now have the following a posteriori estimate. So after k iteration, the arrow xk minus r we know is bounded by ak times the initial arrow. And utilizing this formula here, then we have ak over 1 minus a times the distance between the initial guess and the result of the first iteration. So why is this estimate interesting? Well, this gives us an idea of how big is the error at the kth iteration, because the real root, the fixed point r here, we don't know. What we do know is x0, x1, this is what we can compute. Using the distance between these two and knowing the property of the g operator, in particular the constant a here, then we have an estimate of the error at step k. That shall be bounded by this coefficient here times the distance between the first iteration result and the initial one. One can also manipulate this to get the following, that is, the error at step k is bounded by a over 1 minus a times the distance between xk and xk minus 1. So this one can compute. Using that, and it gives you a measurement, an idea of how far away you are from your result, from the fixed point. We now give some comments. So in practice, the function g is rarely contractive over the whole domain because it's a nonlinear function. So one would assume that g is contractive in a neighborhood of a fixed point r. In that case, if the initial guess x0 should lie in this neighborhood, then the iterations would converge to the fixed point. However, given fx equals 0, it is not easy to construct the function g, let alone identifying a good initial guess. Let's take an example. Consider the nonlinear system f given as follows: x squared plus y squared minus 5 equals 0, x times y minus 2 equals 0. One can easily verify that there is a solution, x equals 2 and y equals 1. So this is one of the solutions. We now define a vector function g as follows. So g will be, the first equation is x minus, this is taken from the function f, but then we divide it by 4. The reason will be clear later. And the second equation is y minus, this is taken from f, but then we divide it by 2. Then the fixed point for xy equal gxy is the following. So the first equation will be x equals this expression in g, and the second is y equals, this is taken from g. So it's clear then, you see x would cancel x, y would cancel y, and get rid of the factor 4 and 2. This simply is equivalent to the function f equals 0. To get an idea of if g is contractive, one can compute the eigenvalues of the Jacobian matrix for g. That will give you an indication of the contractive property of the value a, and the vector norm will be the regular Euclidean vector norm. So performing the partial derivatives of g, we obtain this Jacobian matrix. we are interested in the Jacobian matrix near the fixed point. So let's evaluate it at x equal 2, y equal 1, which is the fixed point. Plug in those values, I get this matrix, which is 0, 0 on the diagonal and negative half on the other two. One can compute the eigenvalues, and you will find two of them. Lambda 1 will be negative 0.5, and lambda 2 is 0.5. And we see that both eigenvalues will have absolute value less than 1. So this indicates that A would be 0.5 approximately near the solution, that is near the fixed point. So if you choose an initial guess not far from it, the fixed point iteration should converge. Here is a Matlab code. This is a Matlab code specially designed for this problem. It's not a general code for solving systems. Okay, let's take a look. So here are just some initializations. I choose initial guess, x 1.5, y is 1.1, not far from the fixed point. Max number of iterations 20, tolerance 10 to the negative 4, initial error set to be 1. This is the count for the iterations. Then we go into a while loop, and as long as the number of iteration is less than the max and the error is still too big, we do the following. And this is to perform one step of fixed point iteration. And then we compute the error. The error is the Euclidean norm square. And then after that, we update. We put the xn back to n, yn back to y. And we increase the number of iteration by 1. And at the same time, we display the result of iteration step, the x value, the y value, and the arrow. And now this is the output of that program. We see that the iteration ends after 5 steps, starting from the initial guess, and this is the result after 1 iteration, and this is after 2. And after 8 iterations, the error is 0.000094, which is less than our tolerance. Okay, so we see that when your G is a contractive mapping, when your initial guess is not far from the fixed point, then this converges. And it's not a very fast convergence, and in fact it's just a linear convergence. Now it is interesting to observe that x equals minus 2, y equals minus 1 is also a fixed point for G. It's very easy to verify that. But unfortunately, if you try to locate that one, the iteration does not converge. Even you start with the initial guess very close to it. So here we run some numerical simulation with the same code, but with a different initial guess. So the initial guess is actually negative 1.9 for x, that's very close to negative 2, and y is negative 0.99, that's very close to negative 1. And we see that this is the output of the program, and we show it to up to 15 steps. We didn't show more because you see that even though you start very close to this fixed point, and eventually the solution drifts away and it gets close to the other fixed point, which is x is 2, y is 1. So it will never converge to this fixed point even though you start right next to it. Now I leave it to the students. You are encouraged to verify that one of the eigenvalues of the Jacobian matrix evaluated at the point x negative 2, y is negative 1 has absolute value strictly bigger than 1. And that means that G is not contractive at that fixed point. And second, I also challenge you to come up with a different fixed point iteration that would make it converge to this fixed point. Give it a try. That's all for this video. Hope you enjoyed it. Thanks for watching and see you next time.